To better understand the EM algorithm, let's consider one example. And that example is going to be a mixture of two Gaussian distributions. So, two-component Gaussian mixture. And for that distribution, the density of the mixture is going to depend on 5 parameters. So we're going to have first a weight that corresponds to the first component. And that component has a Gaussian distribution, 2 pi sigma exp of minus 1/2 x minus mu1 divided by sigma square. And then, because we have only two components, the weight associated with the second component has to just be 1 minus omega. And again, 1 over the square root 2 pi sigma exp minus 1/2 x minus mu2 divided by sigma square. So as you can see, it has two components, this mixture. Each one of the components is Gaussian. The main difference is that we allow the locations of the two components to be different, but we keep the variances of those two components the same. So this is a particular case of a mixture of two normals where we're forcing the variances to be the same. So, and if we think about it in terms of the notation that we had been using before, then what we're doing here is essentially saying that our y of x given theta just takes the form theta k, takes the form 1 over the square root 2 pi sigma exp minus 1/2 x minus mu k divided by sigma square. And essentially, this theta k corresponds to mu sub k and sigma together. So this, in this case, this is a vector that has two components that corresponds to those two parameters in the Gaussian distribution. So once we write the model in this way and we recognize what our g function is in this case, then it's very easy to write the weights for the EM algorithm. Those be I, in this case, 1 at iteration s. And remember that those are essentially an application of Bayes' theorem. So it just tells me what is, if I knew what the parameters are for each one of the components, in this case, what is the probability that the observation was generated from component 1. So that, in this case, is simply omega 1 over the square root 2 pi sigma s exp of minus 1/2 x sub I, because now we're talking about observation I, minus mu1, and this should be hat and s, hat and s, sigma hat s square. So this is just this kernel G evaluated in the current maximum likelihood estimate for the parameters. And this has to be divided by, first of all, the first quantity, omega hat s, 1 over the square root 2 pi sigma hat s exp minus 1/2 xi minus mu1 hat s divided by sigma hat s square, plus now the kernel for the second component and the associated prior probability. So this is 1 minus omega hat of s, 1 over the square root 2 pi sigma hat s exp of minus 1 over 2 sigma hat. Excuse me, I'm going to put it inside the so minus 1/2 xi minus mu 2 hat s divided by sigma s hat square. So this is the form of the weight associated with the ith observation and the first component. And of course, we need also bi2s. And in this case, because there are only two components, we know that that's just 1 minus bi1s. So once we have this calculation, it's very easy to get what is the weight associated with the second component for that same observation. The next thing that we need to do is write the Q function for this particular model that we're going to optimize. Remember that the Q function is a function of the parameters. So in this case, omega, mu1, mu2, and sigma, given the current estimates of those parameters. So given omega hat of s, mu1 hat of s, mu2 hat of s, and sigma hat of s. Okay. So, and if you remember, what we're doing here is taking the log likelihood of the full data likelihood, taking the expectation with respect to those membership indicators, that is basically the V's that we just wrote down. And that gives us a function for the new, what the new values should be given the previous values. So that's why the algorithm is iterative. So just using the expressions that we had derived before, we know that this is going to be equal to the sum over the observations, because it's the log likelihood. And we have two pieces. The first piece has to do with component 1, so it's going to be bi1 of s. That multiplies the log likelihood, so that's logarithm of omega plus the logarithm of the likelihood, but that's minus 1/2 log 2 pi minus log of sigma hat, sorry, log of sigma, minus 1/2 xi minus mu1 divided by sigma square. That's the first piece. And the second piece comes from the second component, so has bi2 of s log of 1 minus omega minus 1/2 log 2 pi minus log of sigma minus 1/2 of xi minus mu2 divided by sigma square. So this is the function that we need to optimize. This omega hat, mu1 hat, mu2 hat, and sigma hat are hidden in the B's that we just computed. So I'm not writing them explicitly, but they are inside these two B's. And so that's how we are conditioning on them, because we're using them to compute these numbers. And now what we need to do is we need to maximize this function with respect to omega, with respect to sigma, with respect to mu1, and with respect to mu2. Let's start by computing the derivative of q with respect to omega and making that equal to 0. Well, in this case, the derivative of q with respect to omega is very easy to compute, because this is just a linear function. So when I go in there, I'm going to get the sum from 1 to n. I'm going to get bi1 of s. And now I need to do the derivative of all of this, but the derivative of all of this, the only piece that depends on omega is the log of omega, so that gives me 1 over omega. And then when I go to the second piece, I'm going to get bi2 of s. And again, I just need to do the derivative of this, and the derivative of this is just the derivative of the log of 1 minus omega, which is 1 divided by 1 minus omega, multiplied by a minus 1 because of the internal derivative here. And so I need to make this quantity equal to 0. So that implies that the sum from 1 to n of bi1s divided by omega has to be the same as the sum from I equals 1 to n of bi2 of s divided by 1 minus omega. And this just comes from, so this minus makes this plus a minus, and I'm just moving the expression to the right-hand side. So another way to write this is to say that omega divided by 1 minus omega has to be equal to, move this there, so I have sum from 1 to n of bi1s divided by the sum from I equals 1 to n of bi2s. And with a little bit of additional algebra, we just get to omega has to be equal to the sum of the bi1s from 1 to n divided by the sum from 1 to n of, again, bi1s plus bi2s. But remember that bi1s and bi2s have to add up to 1. So we defined one as 1 minus the other. So that just means that this expression down here, it's just, so each one of the terms is equal to 1, and I'm summing n of them. So I just get 1 over n sum from 1 to n of bi1s, which has a very nice interpretation. If you think about what this quantity is, this just represents the average probability of all the observations that belong to component 1. Let's compute now the derivative with respect to mu1. And I'm just going to do mu1 because the computation for mu2 is going to be pretty much identical. So to compute the derivative of q with respect to mu1, it's going to be very easy. So we have the sum from 1 to n of bi1s. And now inside here, the only term that depends on mu1 is this term here. And down here, there is nothing that depends on mu1. So what we get is minus 1/2 2 from the exponent, xi minus mu divided by sigma. And we need to make this equal to 0. Now, these two terms can cancel out. The minus sign, you can just reverse signs in here. In sigma, we know that it has to be greater than 0. So we can, if you will, move it to the right-hand side multiplying. So this whole expression can be somewhat simplified by saying that what we want is the sum from 1 to n of bi1s times mu minus mu1, very important, minus xi has to be equal to 0. But now this is very easy to resolve. So this just implies, if I break this into both sides, we have the sum from 1 to n of bi1s multiplied by mu1 has to be equal to the sum from 1 to n of bi1s multiplied by xi. And mu I doesn't depend on I, so it can just come out of the sum. And that just leaves me with mu sub 1 being equal to the sum from 1 to n of bi1s xi divided by the sum from 1 to n of bi1s. So the expression has a very nice interpretation. So you're looking at a weighted average of the observations. The weights are given by the bi1s. And if you remember, this is just the probability that the observation was generated by that component, our current estimate of what that probability is. So observations that are more likely to come from component 1 have a heavier weight in the weighted average for the mean of the component 1. So observations that are in some sense closer to the current center or our current estimate of the center of the component have a higher weight in terms of computing the next value for that center. And the expression for mu2, it's going to be very, very similar. The main difference is going to be that instead of using bi1s in this expression, you're going to be using bi2 in those expressions. And I suggest that you do the calculation and you make sure that you see that you get exactly the same expression with that small change. To complete the algorithm, we still need to work what is the new maximum likelihood estimator for sigma. To do that, we need to compute the derivative of q with respect to sigma. And now we have to be a little bit careful because sigma actually appears in a number of places in the expression. So we have, as always, our sum over the observations. We have bi1 of s. Now, this term and this term do not depend on sigma. So we have minus 1 over sigma is the derivative of this piece. And then we have minus 1/2. Now, this expression, sigma appears in the denominator, and it's a square. So we can think about it as sigma to the minus 2. That brings down a minus 2, 1 over sigma to the cube, and leaves us with xi minus mu1 squared. So that is the first piece of the expression. The second piece is going to be very similar. We have bi2s. And again, the first two terms do not depend on sigma. The third just gives you minus 1 over sigma. And then we have minus 1/2. Again, minus 2 coming from the sigma to the minus 2. 1 over sigma to the cube. Xi minus mu2 squared. And we need eventually to have this expression equal to 0. OK, so let's simplify this a little bit. And to do that, let's pull together terms that look the same. So let's pull the terms that have 1 over sigma in them together, and then the other terms. So we have the sum from 1 to n of minus 1 over sigma that multiplies bi1 of s plus bi2 of s. And then the other term, again, looks very similar. So we're going to have minus 1/2 multiplied by minus 2 is going to end up giving me a plus. Just like here, the minus 2 multiplied by minus 1/2 gives me a plus 1. So I have plus 1 over sigma cube that multiplies bi1 of s times xi minus mu1 squared plus bi2 of s that multiplies xi minus mu2 squared. Okay? So just reorganizing the terms. Now, this is very nice because if I want to make this equal to 0, one of the things that I can do is I can cancel this with the cube, And so I get a 2 in here instead. And one term is negative, the other one is positive, so I can just move them to opposite sides of the equal sign. So I'm going to end up with the sum from 1 to n of bi1 of s plus bi2 of s has to be equal to the sum from 1 to n of, 1 over sigma squared, bi1 of s times xi minus mu1 plus bi2 of s xi minus mu2. Well, now, and this ends up being very simple now, so I can move the 1 over sigma squared to the other side. The other thing that I know is that these two guys add up to 1, just by definition. So at the end, we get that sigma squared has to be equal to 1 over n sum from 1 to n of bi1 times xi minus mu1 square plus bi2 xi minus mu2 square. And again, this has a very nice interpretation. All I'm saying is that it is in some sense a weighted average of the variances that you would get by computing only with the mean 1 or only with the mean 2, and the weights are based on how likely the observation is to come from each one of the two components.